Hello and welcome to Tech Simplified TV. In last episode, we have discussed about VLSI interconnects and their real-time behavior. Knowledge about interconnects is very important as more than one real-time reliability issues are connected with them. In today's episode, we will discuss about interconnect delay modeling and we'll try to understand which approximation is well suited for which situation. If you are interested, stay tuned till the end of the video. Now let's take a look at the pointers we are going to discuss in today's episode. First, delay in IC. Second, delay models. Then lumped C model. Then lumped RC model. Next, pi and T models. Next, Elmore Delay Model. Then RC tree network with Elmore delay. RC chain with Elmore Delay Model. Distributed RC line model. Transmission line model. And lossless transmission line model. So let's move to the first slide. Delay in IC. Input to output delay in IC has two components, gate and interconnect delay. In previous episode, we have discussed about delays, that when signal is applied at the input of the IC, it takes some finite time to get the desired output, expected desired output at the output pin of the IC. So that is the delay, input to output delay for an IC. And this delay in IC has two components, one due to gate or cell, and another component of this delay is contributed by interconnect. We call it interconnect or wire delay. First, gate delay. Signal transmission through a gate is not instantaneous. That even signal transmission, this is a NOT gate, input of this NOT gate, and get the desired output, we don't get that instantaneously. It takes finite time shift. When this 1 to 0 transition is happening, the desired output should be 0 to 1 transition, and we get it, although after some time delay. That is gate delay. The time required for signal to travel from input of the gate to output of the gate is gate delay or propagation delay. We also call it propagation delay. The figure shows gate or propagation delay of a NOT gate. Output changes after a delay of delta with change in input. As we can see, gate delay is not equal for high to low and low to high transition. This high to low or low to high transition, the delay is not exactly same. We will discuss it in some later episode. Today, we will mostly concentrate on wire delay or interconnect delay. Now, let's move to wire delay. So, wire delay interconnects or wires connecting active devices at delay while carrying signal. This is wire delay. So, between two gates, there is gate 1 and there is gate 2. They are connected by wire. So when signal is applied here, we get desired output, but the desired output will not reflect or will not reach from this point to that point instantaneously. We know why. Because of interconnects add delay, because of their parasitic effects. So there is a finite time, and that finite time is denoted by this delta. That is the wire delay. Wire delay is also known as transport or flight delay. Wire delay becomes dominating with higher operating frequency, that is lower device dimension. Now that is a table. In mid-80s, gate delay was 85% and 50% of the total delay was contributed by wire delay. While we have moved to more small devices in mid-90s, the ratio became 50-50. Now post-millennium, the situation has worsened so much that gate delay or cell delay only contributes 20% of the whole delay, whereas 80% comes from these wire delay. So, although we have today discussed this gate delay, what is gate delay and wire delay, we will mostly concentrate our today's episode on wire delay. So, let's move to the next slide. Delay models. We have already discussed about cell or gate delay and wire or interconnect delay. So, let's know the name of the delay models. NLDM, ECS and CCS. These are delay models for gate or cell delay. And for wire or interconnect delay, we use lumped C model, lumped RC model, distributed RC model, transmission line model, wire load model. Now, NLDM is nonlinear delay model, ECS is effective current source model, CCS is composite current source model, these all delay models and their data all are mentioned, usually get mentioned in leaf file. We have episodes on characterization. Link is provided in the description. Watch the episode. You will get better and clearer idea about all these models. So since today's episode is concentrated on wear or interconnect delay, it's just what I'm doing is just touch base for these names and all, but actually we will discuss in detail about these models. RC network and gate delay modeling. RC circuits are frequently used to model the timing characteristics of ICs. Here also we will talk a little bit about gate delay modeling because of this RC network. Why RC network? In coming few slides we will discuss in detail about RC network and delay modeling. So here we are just giving you an idea why RC network. In gate delay modeling also we use RC network. RC circuits are frequently used to model timing characteristics of ICs. When one logic gate drives another gate, the input circuit of the second gate can be modeled as an RC load. For electrical modeling, we do the approximation of the active devices as passive device and then do the calculation. The propagation delay through the first gate is calculated by assuming V in as ideal square wave and the RC load. These models, we just try to be as close as possible to the real-time scenario. This works really well for EDA tool and design purpose. Gate delay is inversely proportional to the switching speed of the gate. So obviously, if delay is high, or it will take a lot of time. If delay is less, though, the gate will switch quickly. Next, RC network and wire delay modeling. A wire can be modeled as many cascaded sections of simple RC circuits. When a square wave is applied to one end of the bus, it takes time to propagate. This delay time due to wear can be calculated based on value of R and C in each section and number of sections used to model the wear. The longer the wear, the more sections are needed for accurate model. Now, why RC network is important? It gives us a good approximation of a long wear. A wear can be modeled as a many cascaded section. So first, what actually we do, we take a smaller model of RC and keep on repeating that thing again and again and again. When square wave is applied to one end of the bus, it takes time to propagate because of delay. Obviously, the delay time due to wear can be calculated based on values of R and C in each section. So we break it in smaller section and calculate and then do the summation. We will see it later. The process, this is the basic process. And the number of sections used to model the wear. So if the number of sections of such RC basic structure sections are more, the result will be bigger number. So delay will be more. The longer the wear, the more sections are needed for accurate model. Now, wear load model, we said that wear load model is used to estimate delay based on area and fan out. Semiconductor vendors develop wear load models used in pre-layout design cycle. So here we will not consider wear load model in our discussion in detail. Whatever timing model and estimation we are discussing today, this is completely for post-layout design cycle, that is PD. Wear load model we will discuss in some other episode because that is not part of physical design. So let's move to the next slide. Now, lumped C model. Circuit parasitics of a wire are distributed along its length and are not lumped into a single position. So at every point, when a signal travels from one point to other, it faces effect of parasitic at each point. Although for our ease of work, we adopt some model. One of them is lumped C model. Although we know that is the parasitic is not lumped into a single position, but still we follow such rule for ease of calculation. Lumped model is considered in a circuit where single parasitic component is dominant. If a single parasitic is dominant, in many cases in maths we do it keeping one parameter, tending it to 0. So we keep one parameter off there so that the calculations become easier. Interaction between the components is small. And third, one aspect of the circuit behavior is considered. We are considering single parasitic component is dominant, others are not. Interaction between components is small. One aspect of the circuit. So when which one is predominant, we will consider that one and accordingly we will model. This is the driver. This is V out and that happens on the higher node. more matured node, capacitive action is more predominant compared to the resistive parasitic. So there we can approximate that there is no resistance, only capacitive actions are there, that is modeled by some capacitance. So this is the driver and this is the V out. So that scenario is modeled as this is the signal. Then when it's on, we consider it as a resistor, and altogether all capacitance are lumped, their values are lumped into one, and that is the V out. This is the easiest or the simplistic model. Effects of parasitic can be described by an ordinary differential equation. That's one point. If parasitic R is negligible and circuit is operating in low to medium range, only capacitive component is considered. Distributed capacitance lumped into single capacitor. There is a condition that it's operating in low to medium range, and resistance is negligible if the technology node is on the matured side. That is lumped C model, suited well for older technology node where wires were wide. High cross-sectional area A means less R. So resistance is not that dominant. In this model, where is equipotential region and where does not introduce any delay due to resistance. Impact on performance is introduced by loading effect of the capacitor on the driving gate. This capacitive lump model is simple and effective. Model of choice for analysis of most interconnect wires in older techno. For older technology nodes or matured old technology nodes, this is the most choiceable model. Now let's move to the next slide. Lumped RC model. Lumped RC model is used when wire length L is greater than few millimeter and resistive component is considerable. With scaling, where cross section is reduced and R become considerable. Lumped C model is inadequate because the assumption for lumped C model was that R is less. If R is increasing, then R is also becoming a considerable and dominant factor. So we cannot use lumped C model there. Now interconnect is modeled with resistive, capacitive or RC model. Multiple approaches are there depending on complexity and operating condition of the circuit and verified with accuracy of the result. For lumped RC model, there are multiple approaches depending on the complexity and operating condition. And now lumped RC model, the total resistance of each wire segment is lumped into one single R and global capacitive is combined into single capacitor C. Within driver and receiver, this is the model. Total resistance of each wire segment is lumped into one single R and global capacitance is combined into single capacitor C. Again, approximation, although they work really well, this model is pessimistic and inaccurate for long interconnect wires, which are more accurately represented by distributed RC model. If its interconnect wires are really long, then more accurate model is presented by distributed RC model. So next slide, RC networks. Studying lumped RC network is important as the distributed RC model is complex and no closed form solution exists. Distributed RC model is a better approximation, although they don't have any closed solution and solving is complex. The behavior of the distributed RC line can be adequately modeled by a simple RC network. So when the model is accurate, although solving it as a complex situation, we go for another approximation. So we approximate it as simple RC network and then try to find the solution. A common practice in the study of the transient behavior of complex transistor wire network is to reduce the circuit to an RC network. We reduce them to a simple RC network. Analyzing such a network effectively and to predict its first order response is important for designers. We try to keep the answers simple. So we try to predict the first order response of the system. Two popular network are tree network and RC chain or ladder network. This is the tree network. This one. This is S or input node. From there, at each node, they are grounded by a capacitor. And this is a ladder or chain structure. These two networks are popularly used in modeling. Now let's move to the next slide. Pi and T models. The distributed RC delay can be modeled by breaking up a wire into one or more segments and using lumped model for each segment. Getting solution to distributed RC delay model is complex and tough, so we approximate it by simpler form of RC network. What we do that we break up a wire into one or more segment and using lumped model for each segment. Next, popular lumped models are pi and T models, named obviously after their shape. There is another model, L model, which is not really good approximation. That's why we have not included it here. R and C depend on length of the segment. We are breaking the wire in smaller segment, and for each segment we are applying that lumped RC. So resistance and capacitance of that segment is lumped into single R and single C, and then it become a network of series of R and C. So value of R and C depend on length of the segment. More the segment, value keep on adding. Pi and T model are both good models, although pi model is slightly more convenient because of fewer circuit nodes. Most circuit simulators have built-in distributed RC model of high accuracy. So these models are, everything is included in circuit simulators. The pi model, pi 2 model, pi 3 model, as we can see, T, T2, T3 model, these are models, popular models. So let's move to the next slide. Elmore Delay Model. Elmore Delay Model is derived originally in 40s for circuit applications and applied in 80s for RC trees. Elmore defined delay through linear network as the first moment of network impulse response. It gives the first order solution. The Elmore delay formulas are immensely useful and simple model, easy to use model. Layout people use in algorithms single time constant. The solution we get is basically single time constant solution and more accurate compared to simple length based scheme. Although it's not super accurate, it requires some later verification with higher order model that incorporate more than one time constant. Simple RC model provides general approximation of timing behavior of digital integrated circuits. Elmore delay model is used in order to improve accuracy of RC model. So RC model provides general approximation of timing behavior of a digital IC. Elmore delay model is used to improve the accuracy. We need to be closer, as much as closer possible to the real-time scenario. Here the RC segments made up of series resistance Rn and capacitance Cn are created. Think of current like real water flowing in tree. This is current in, this branching out. It's a tree-like structure, main branch, then smaller branch, then going towards leaf. From any component of tree looking at the source, it's upstream, and look towards leaves, it's downstream. So next, RC tree network with Elmore delay. Now we will apply Elmore delay on RC tree network to get the result. Wire branching into many destination modeled as RC tree. A wire branching into many destination like this, we model it with RC tree. It's a tree of resistors obviously. Root of the tree is at source node S, where input signal is applied. There is no loop. At the branch end, output is measured. Each intermediate node is grounded with a capacitor. As we can see, there exists a unique resistive path between the source nodes and any node I of the network. There is an unique resistive path between any node and the source node. Like S and 2, the path is this. S and 3, path is this. S and 4, R1, R3, R4. And to I, R1, R3, RI. This is the path. The total resistance along this path is called the path resistance, RII. The path resistance between the source node and node 4 is expressed as R4. So this is the node 4. So what would be the path resistance? When signal will travel from this point source node to this node 4, they will travel through R1, R3 and R4. The path resistance of the shared path can be expressed as resistance RIK. There are shared path resistance is calculated by a formula that summation of Rj, where k is from 1 to n. Basically, the expression is like this is the expression, and this is effective resistance between the input and node k in common with path between the input and node I. If we want to calculate shared path resistance between two different node k and I, that would be, we have to take effective resistance between the input and node k 1 and effective resistance between input and path I, and we have to take common of these two. like this. Rj belongs to path S to I, intersection path S to K, not union, intersection. I hope we all remember the set theory. If that is a set and that is a set, this is the intersection, a common point. So using above formula, Ri4 is R1 plus R3. How it is happening from, so Rs to Ri is R1, R3, Ri. And S to 4 is R1, R3, R4. So common part is R1, R3. That is the shared resistance of these two nodes, 4 and I. Similarly, 2 and I, it's the common resistance is R1. So this is the Ri2 equal to R1. The Elmore delay from source to node I of an RC tree is given by summation of Rki and Ck. Ck capacitor on node K and Rki shared resistance between node K and I. So first calculate this Rki calculated. Now this Elmore delay model for network is R1 C1, R1 C2, R1 plus R3 C4, R1 R3 Ri Ci. This way it goes. So let's move to the next slide. RC chain with Elmore delay model. It's a special case of RC tree network, non-branched RC chain or ladder. In digital circuits, similar structure is found, represents an approximate model of a resistive capacitive where the delay component of node 1 is C1 R1. R1 is the total resistance between node 1 and the source. Node 1 and source, this is the total resistance. And C1 and R1. Then node 2, R1 plus R2. And delay is summation of capacitance I into resistance from source to capacitance I. So if that is the ith capacitance and the ith node, so R1 C1, R1 R2 C2, this way it goes, and that R1 R2 R3, then Ri C1, this way. This gives the right answer for all values of C and R unless these both have equal to 0. Its only equation is that is correct in all the limits. Now let's move to the next slide. Distributed RC line model. Distributed RC line model is more appropriate model. R and C stand for resistance and capacitance per unit length. We know that parasitics are distributed across length. Here the resistance and capacitance are per unit length. The voltage at node I of this network can be determined by solving partial differential equations. C delta L del Vi del T equal to Vi plus minus Vi plus Vi minus 1 minus Vi divided by R del L. By reducing delta L asymptotically to 0, we will assume that delta L tends to 0, and then we will get that RC del V del T is equal to del square V del X2, where V is the voltage at a particular point in the wire and X is the distance between this point and the signal source. These equations are difficult to use for ordinary circuit analysis. The distributed RC line can be approximated by a lumped RC ladder network, which can be easily used in computer aided analysis. So again we are taking different approximations, like first delta L will tend to 0 and then it will become a function of RC, and we will try to approximate it by a lumped RC ladder network because it's easier to solve and then use in computer aided analysis. Let's move to the next slide. Now transmission line model. Inductance is also there. The inductance is distributed over the wire like R and C. A distributed RLC model of wire known as transmission line model becomes most accurate approximation of the actual behavior. In transmission line model, a signal propagates in the interconnection medium as a wave. In the distributed RC model, where the signal diffuses from the source to the destination governed by the diffusion equation, in the wave model, a signal propagates by alternatively transferring energy from electric to the magnetic fields or equivalently from capacitive to inductive modes. So, when we consider RLC, R, L and C, it's a transmission line model. We are considering a point X along the transmission line as the figure is showing here. At time t, the following set of equation holds. These two equations we get two partial equation, del V del X equal to minus IR minus L del I del T and del I del X equal to minus GV minus C del V del T. Assuming that leakage conductance G equals to 0, which is true for most insulating material, and eliminating the current I yields the equation. It's reduced to this equation where R, C and L are the resistance, capacitance and inductance per unit length respectively. This transmission model has more parameters and more complex. Let's move to the next slide. Now lossless transmission line. For the lossless transmission line, R is 0 and the previous equation simplifies to ideal wave equation. So R components is also 0, so that is reducing to this equation. And if we apply step input, so that propagates with speed v, which gives a solution of this L and C. Values of both L and C depend on the geometric shape of the wire. Their product is constant and is only a function of surrounding media. The propagation delay per unit wire length of transmission line is the inverse of the speed. So this is the equations for lossless transmission line. Today we will conclude here. So that we all had for today's episode, and today we concentrated only on the delay models for interconnects. We have not included cell delay here. That's altogether a different discussion and we will cover it in some other episode. Thank you for watching up to this point. If you have any question or query, please put it as comment. If you have any dislike, also put it as a comment. Don't forget to like, share and subscribe. Thank you again and bye for today.